Let me try to share my slides. And I think we're good to go. 1 second. Okay, so I'm very happy to take questions whenever you want. Just since I'm full screen, somebody has to say something. The talk will be about 45 minutes, I hope. What I'm going to talk about is two of the recent works we did. One is trying to get more geometry and more structure into the way neural PDE solvers operate, and the second one is a bit of a general approach how to achieve better baselines towards a multi-spatial-temporal generalization, leveraging many ideas from computer vision and so on. I think the most of the time I will spend with the first paper, but we'll see how it goes. I will start with a very quick introduction into PDEs and especially into how PDEs entered the deep learning community and how deep learning is seen to help accelerate PDE solving.
So Johannes, just a note, your slides didn't change. They're supposed to.
They should. Yeah, I'm already on slide 3. That's unfortunate.
Okay, now it's changed to slide 3, but
you still see you.
So it's not in full screen mode right now.
Yeah.
It did now change to slide 3, but
when I go full screen, basically it doesn't change, right? Yeah, okay, then I have to stop sharing and go full screen first. And then, sorry for that. It should do something now.
It's changing now.
Okay.
Yeah, perfect.
Fine. So whenever, I mean, obviously PDEs and ODEs are everywhere and omnipresent. I mean, from weather modeling hard dynamics, plasma physics, and so on and so forth. It goes from the very microscopic to the macroscopic scale. And of course, different phenomena come with different challenges and so on and so forth. If we map that basically to the PDE setting, personally, I make the distinction between 3 kind of problems. The first is kind of like the weather prediction problem, where we have a massive amount of data, whatever massive means, but lots of data recorded. And we basically have no underlying equation. We know that it's kind of fluid dynamics, but really the underlying equation is alluded to us. Then we have this phenomena like plasma physics, where we kind of know the equations, but there are many different equations, and the real way of how these terms fit together are still unknown, and whenever we change things, equations might change. So this is a bit in the middle, and generating data here is pretty costly. And then we have this airplane design example where we know equations very well. We know that this Navier-Stokes equation, we know these boundary effects and so on and so forth. But doing the simulation, doing the calculations is extremely costly, and generating data at the fine scale is extremely costly. So here it's really about getting better generalization and so on. But we are not fighting against most other methods, like usually it's done in the deep learning setting, where I just try to beat the benchmark from the institute next door. But we're really fighting against 200 years of numerical solvers. I mean, this is a very rich history, and people are doing extremely nice work there. And one has to be a bit humble and look into these books and into this expertise what people are doing there. I mean, in general, this ways of how numerical solvers should work, they come with a lot of conditions. They should be accurate, they should be stable, they should be fast, they should be easy to use, and the best deliver uncertainties, and all should come with low computational cost and strong generalization effects, which is of course a very, very hard thing to do, and that is where machine learning is hoped to help. And for me, when I started as basically the introduction or the way into neural PDE modeling, it was very, very helpful to write down a PDE in a way that the time dependent terms are on the left and all other terms are on the right. So maybe I should also say that most interesting phenomena, at least for me, are time dependent phenomena where systems move over time, where you have like weather forecasting or fluid dynamics and so on and so forth. And in this time-dependent PDEs, we have these terms which depend on the time on the left and all other spatial dependent variables on the right. And together, all these derivatives and terms with the initial condition, so the condition of the system at the starting point and the boundary conditions at the boundary of your domain, basically give the PDE. If everything if the time is on the left, it's normally can be regrouped in a way that it's just the first order derivative. So basically what many of the solvers do in a simplified way, they try to estimate all these derivatives on the right by some numerical schemes. You can use a finite difference schemes or some advanced schemes, but in the end, it boils down to estimating these terms, plugging them back into the right term, and then updating the left. That is a bit of how personally I see numerical solvers, and then you can start to say, well, I want to replace the right part of this process. I want to replace the left part, which hardly brings a big gain because these Runge-Kutta solvers are so fast, or I want to replace the whole solver at once. And while doing that, basically there are many different directions and many subtleties. As there are numerical challenges, there are different ways of how to inform these problems. But in general, I would say there are two mainstream approaches which are worked on. The one I boldly call them pin-like approaches, named after of course the pin paper, so the physics-informed neural network paper, which really directly learn the solution function of the PDE. So the idea is that you have a function which depends on variables. You use this function, of course, will then be presented as a neural network, and you use this function to do some predictions, do automatic differentiation, and use this automatic differentiation basically to fill up the equation and to get some residual errors. So whatever doesn't fit into the equation, basically, which is given, is your error. So for these pin-like approaches, it's not necessary that you have data. You can basically directly learn the function, but you just learn it for one data point. So you have one set of coordinates, one time point, and you get one output. Of course, it can be that you have multiple outputs when you have different fields and so on and so forth, but it's usually one output in space and time. And then on the second approach, there is operator learning approaches, which map from one space of solution to another space of solutions. And this space of solutions can be seen as an image-to-image mapping. So I have here on the left a bunch of fields, so pressure, velocity, and so on and so forth. And I use these fields to map them to a later state in time. There is basically many, like 70–80% of what people are doing can be characterized one or the other way as operator learning approaches. I think it gets really interesting when one starts to learn to generalize to different grids. So when the input grid and output grid are not the same, when you really generalize across basically very different ranges of grids, when you generalize across boundary conditions, when you generalize for different conditions and parameters, saying that the initial condition here on the left with the different parameters input gives you a completely different output. But this is something which is really hard and where current solvers are struggling. I will say more about that in the second part of my talk. And the work I'm presenting today is on operator learning. And with that, we directly come to the first paper, and this paper is about basically modeling connections between different fields. It is, for me, it was always a bit strange that when you present vector fields to a neural network, you basically chop everything as a channel and treat everything as a channel. And that is especially interesting if you look at phenomena in physics and in nature. For example, in a very simple weather prediction, as it is done here with the shallow water model, that's one of the simplest weather models. But what you have is on the left a scalar pressure field. So at every point you have a pressure value, and on the right you have a velocity field. So at every point you have a wind vector sitting. And what is happening is that if the pressure changes on the left, so if there's some gradients, the wind, of course, starts to flow towards this low pressure regions. And this, of course, again, causes the pressure to change, and that again causes the wind to change. So these like two fields, where one field is a scalar field and the other one is a vector field, are very, very strongly coupled. And it feels a bit unnatural to cut this coupling off and treat them just as channels. And that is basically how this work started, because a very natural way, or one of the most well-known operator learning methods, is the Fourier neural operator, which basically is using a fast Fourier transform on an input, and on this the fast Fourier transform basically gives you a bunch of Fourier modes, which you modify via some weight multiplication before you go back into the spatial domain. So that instead of doing a convolution in the spatial domain, you do a weight multiplication in the Fourier domain. We will see later how this relates to each other. But it is important in that point, because this was the starting point for us to think about that, for me to play around and always having this this Fourier transform in my head, because the Fourier transform can only be done on scalar fields. So whenever you have a vector field, it's not clearly defined. So you basically cut the x component off and treat the whole x field as a scalar field, and then you do a Fourier transform. And that is basically what I tried out. So I had this very, very simple toy example. So I had a bunch of vectors which form like these curves, and on a grid of dimension 32 times 32. Those who are familiar with deep learning, like tensors, that's the way this is written in a tensor. So the batch dimension is, of course, 1. The channel dimension is 2, because, well, we have an x dimension and a y dimension. So each of these arrows has a value pointing towards x and a value pointing towards y. And then we have 2 dimensions which give the location. And now, normally, what you do when you feed it to such a Fourier neural operator, basically you take a Fourier transform on this x dimension and on this y dimension of this arrow. And I did that, and in the Fourier space, I did some random weight multiplication and I transformed back. The results are a bit unsatisfying, because if you compare the right to the left, it's not, it changes completely. So I mean, that per se doesn't have to be like wrong, or doesn't have to be like bad, but in a way it kind of totally destroys the structure. And I very naively always have this convolution images in my mind, where you slide a filter across the image, and then you basically after the first convolution filter, you can still recognize the original image. It may be a bit blurred, or the filter has detected some interesting things. But here it really seems that the image is totally altered, and it's basically not recognizable anymore. So then I started to do it a bit differently. So instead of encoding that really as 2 different channels, I'm now treating every I basically treat every vector as a complex number. So that means that this dimension, of course, we still have 1 channel, one batch, but we also have now 1 channel, and well, a 32 times 32 vectors. But each of these numbers is basically now a complex number. So each vector can be represented with a complex number. And you can do a Fourier transform on complex numbers. That's actually how it is defined. It's just that what we did before was a Fourier transform just for real numbers. And well, then I do the same trick. I use the same random weights in the weight space and I transform back. And what you suddenly see is, I mean, it's of course distorted and it looks, well, a bit weird compared to the left, but that is of course what you expect when you do a random weight multiplication. But you also see that the structure is much better preserved, and that was kind of what kept me thinking and what started this project. And I started to look around what you can do, and if you start digging and start looking what people did in computer vision with Fourier transforms over vector fields, in some way or the other, you stumble across something like Clifford algebras, because Clifford algebras have this way of extending the concept of scalars and vectors towards objects which are called multivectors. And instead of defining operations on scalars and vectors individually, you define operations on multivectors. And basically, that is what is going on. So a scalar, I mean, everyone I think can imagine what a scalar is. A vector also. I mean, it gets a bit tricky, but when you come to bivectors, so bivectors are kind of plane-like elements. They have an orientation, and they have an area, so to say, and depending on how this if you change the order of the vectors of the bivector, then the orientation changes, so that basically the bivector E2 and E1, if you change E2 and E1, it looks in the opposite, or that's it basically that there's a sign flip. And that is very much what arises in nature when you, for example, describe the curl of a vector field, which usually or the cross product, which usually is represented as a vector, but it is truly not a vector because it transforms differently under mirroring than a vector does. So these are the bivectors. These are the plane elements. And then you have even higher order objects, the so-called trivectors, which are volume elements. What I omitted here and did not tell you that this is an example of a three-dimensional Clifford algebra. So we live in the underlying vector space is three-dimensional because the basis vectors are E1, E2, and E3. They are just three basis vectors. But this already gives rise to three bivectors and one trivector. If you go, for example, one dimension higher, in a four-dimensional Clifford algebra, you have four vectors, six bivectors, and four trivectors, I think. And this, of course, grows with the dimension. For us in that paper, low dimension Clifford algebra were enough, but it gets more exciting if you go to higher ones. And then what was very central to this paper is the so-called geometric product. So this is a bilinear operation between these objects called multivectors. It has all these properties of closure associativity and commutes and distributes with scalar multiplication and over addition. And basically there is a subtle switch from a Clifford algebra in 3 dimension to a Clifford algebra in 2 dimension from the last slide to this slide. So in 2 dimension, you only have a scalar, 2 vectors, and a bivector. And basically, if you think of A and B as 2 multivectors, if you put them together, omitting any point or other symbols, you basically end up with a new multivector of the same algebra, which basically has combined all these base vectors of all these elements of the original AB vectors in a very natural way. And basically that is the idea now, to use this multivector viewpoint, so to go from scalar representation to a multivector representation, and to use this geometric product as an operation which replaces the dot product. And that is a very simple way of how to define a convolution. Because what you now do, if you think of these input fields, which normally you would say these are like 10 channels, or like 8 channels, I think, to be concrete, we can think of these channels as a bunch of multivector channels. So in that sense, we just have 2 multivector input fields, and each of these 2 input fields has a scalar part, a vector x part, a vector y part, and a bivector part. And of course, if these channels have this signature, also the multivector kernels have this signature. So these multivector kernels also consist of multivectors. And then basically, instead of convolving scalar filters over scalar fields, we convolve multivector filters over multivector fields. And the operation of how this convolving is done, the underlying operation, is as written out here, the geometric product. For Fourier transforms, it gets a bit trickier. And that is actually, as I showed in the very beginning, that was the original way of how we stumbled across that. Because these Clifford algebras, they have a very intriguing way of writing out these multivectors. So if you look at this multivector here, I'm sorry, it's a bit small. So you have this scalar part, this E1, which is the X component, this E2, which is the Y component, and this E1, E2, which is the bivector component. You can basically introduce the so-called pseudoscalar. The pseudoscalar is nothing else than the bivector. And if you use this bivector and multiply to basically to these elements, you can write out the expression on the left to something like that. It's very easy to verify because the only thing what you do, you basically use that and write this E1, E2 as bivector, and then you basically have the first and the fourth term. And here you write the A2 plus the bivector. And if you multiply the bivector with E1, the E1s cancel and you end up with E2. So basically that's just another way on the left how to write the expression on another way of how to write the expression on the left. But the nice thing is that you can write this part into two different parts, and both parts have this form of a complex number, and they're actually really a complex number because they're actually really close to a complex number, because if you look some of these properties of this bivector, or pseudoscalar as it is also called, it squares to -1. And so we have an element which squares to -1, and that makes it very close to the complex number. And that is the idea, that you can now treat these really as two different parts which are complex valued. And they have some different properties. The one transforms differently under sign flip than the other, so you kind of have to take care of that. But in either way, you can use such a multivector to put it as a combination of two complex numbers. And this fact is used in the Clifford Fourier transform. So instead of how the standard Fourier transform is done on the left, where you have the bunch of input fields, and you basically do a Fourier transform for each of these input fields individually, you mess around with the Fourier modes, and then you go back. We now basically split this multivector input maps. Remember, we now have maps of multivectors. We split them into these spinor parts in green and these vector parts in red. And then we do a Fourier transform, a complex Fourier transform on those two maps individually. Then we add these modes together to have a mode which consists of a multivector mode, so to say. We do this geometric product operation on these modes. Then we again split the spinor and vector part apart, and we transform back. So that's a natural way of how to extend this Fourier transform over scalar fields to a Fourier transform over multivector fields. And now, if you look back at the example I showed in the very, very beginning, basically what I had there is just the second part. I had a vector field with the vector component X and a vector component Y. I didn't have a scalar component and didn't have a bivector component. But already there, I'm doing it in just writing this vector as complex number, which is nothing else than I'm doing here, is giving the correct result. And that is actually basically, so this vector part really goes into this red part here. And that was the setup. So we had these two layers. The one layer which had basically the task to replace any convolution layer, and the other layer which had the task to replace any Fourier transform layer in neural network architectures. And that's how we tested that on various sets of operator learning tasks. So these tasks are kind of simple. You get an input of t time steps, normally 2 time steps or 4 time steps, and you predict the time steps into the future. And how much you predict in the future is, of course, depends on how difficult you want to have to the task. If you predict farther in the future, it gets more difficult. And how these data sets are designed now is they should have a scalar part and they should have a vector part, and maybe even other fields, because this is exactly what we were trying to model. So we wanted to have this multivector character of fields which are interacting with each other. The first task is as seen on the bottom of this page is a Navier-Stokes equation, very classic. You have the vector field here, so really, I mean, it's a bit too tiny to see, but there are all vectors pointing in different directions. And on top of these vector fields, you have some form of smoke, which relaxes according to these underlying vector fields. And these two fields are coupled via some buoyancy force, which is acting on the smoke, and then the smoke influences the vector field again, and vice versa. But this is a rather weak coupling, so it's a good example to start, because again, we have a multi-vector character, we have scalar and vector fields, but the coupling is not very strong. So still putting the question is if putting that into a multi-vector network would help. The second one is the shallow water equation, which is showed in the very beginning, where we have the scalar field on the left and the vector field on the right. And these are much stronger coupled, actually, as I tried to explain, with the changing pressure. And they are coupled via 3 coupled partial differential equations. And the most interesting one is in 3D, is the Maxwell's equation, where you have the electric field and the magnetic field. But actually, the magnetic field is the dual of the electric field, and the magnetic field can really be described as a bivector. So instead of describing this electric and magnetic field as 6 individual components, 3 for the 3-dimensional electric field and 3 for the 3-dimensional magnetic field, you put them into one multivector. And remember, these multivectors in 3 dimensions, they have 8 components. And you can fill all the vector components with the electric field and all the magnetic components with the magnetic field. And that's really how we got these results, by the way. So the first result, we saw that the Clifford layers were doing better than the standard layers. They were, especially the Fourier transform was doing very nice. But the difference was not that big as expected, because this coupling is not so small, is not so strong. For the weather modeling, the difference was much more pronounced and stronger as expected, because we have a stronger physics connections which we're trying to model. And for this magnetic field, the connection was actually and the difference was pretty strong, which is shown here for various measures. So the 1 step, so how good we are at predicting 1 ahead, the rollout, how good are we if we want to predict 5 steps ahead, and then for the different fields. The orange is the Clifford Fourier transform, the black is the standard Fourier transform. The most interesting thing is that for me personally, I had a bug in the code, as it always happens in such projects, that I exchange the fields of the magnetic field. So basically, the wrong magnetic field got asserted as a complex counterpart of the electric field. And that basically caused the network to not really be better than the baselines. But just by sweeping this, these fields was giving a huge impact, because now the physics kind of are correctly represented. That was very satisfying. And maybe I should end that here with one closer look at the shallow water results, because you should not, well, you should also discuss the interesting parts. And the interesting parts is for the ResNets at low and lower number of trajectories. So maybe I've said now a few things which I should clarify. So we tested 2 types of architectures. The one are resonant architectures, just for the simple reason that resonance architects are basically are just built up purely from convolution. So we could really verify if changing convolution has an impact. And then the Fourier null operator, because these Fourier null operators, they are really strongly based on Fourier transforms. So both of these architecture allow to individually look if these layers make a difference. And you see on the x-axis the number of used trajectories. If we go from left to right, the number of trajectories gets lower. Actually, if one compares these numbers, resonant against Fourier null operator, the resonant is doing much worse, and the reason is it's not able to collect all this global information. But for a low number of trajectories, it also seems that the yellow and the orange curves, so our layers, are really not doing very well compared to the baseline. And that also was quite an interesting insight, because after trying long and plotting all the results and so on and so forth, it seems that for such, like the model itself is not very good, and what it does, it basically just smoothens the data, for which you don't need any inductive bias. Right? But if you increase the number of data, at some point the model gets into a reasonable range of results, so the error goes down, and that is when the advantage kicks in. That's a bit counterintuitive, but the lesson I learned is that whenever we talk about inductive bias, having a strong inductive bias, what we need is actually also a strong model, as the Fourier operator is exactly for that case. But if you have a weak model, basically the good physics inductive bias cannot be leveraged, because the model is just trying to do some smoothing. And that was for me personally, that quite interesting. And with that, I want to go to the second part. This is a paper which is basically we did in parallel, and basically the motivation was really that there is a lot going on in computer vision, and there is this state of the art in image generation, and since like a few weeks there is this text to video modeling, which is just mind blowing, in my opinion. And the way basically all the success stories of all these models is, of course, transformers, which give a good text encoding, and diffusion models, which are the big game changer here. But these diffusion models are very much based on units and on the conditioning. So on the conditioning of the text prompt, which you basically insert into these units. And then the question is, of course, why don't you use units for PDE modeling? Because the way you do this, or these diffusion models, is really by mapping from one step to another step, conditioned on something else. That sounds very much what you do in a PDE, right? You map from one state to another state, conditioned on some parameters. Of course, people use units, but not extensively, and they are not. Most of these units are, or most of these modern units are not so heavily used. So we looked a bit into units, and units are around since 2015. They are one of the most impressive deep neural architecture breakthroughs, in my opinion. What they are basically doing, they have this spatial downsampling and spatial upsampling paths. The interesting stuff is that this spatial downsampling starts with looking at global information, and then it downscales the image to such that it basically looks at the global information, and then it upsamples again, and via this upsampling copies over the parts from the downsampling branch of the unit. And as I said already, it's highly optimized in computer vision. All the tricks have been tried out, and it's doing a fantastic job. And if you compare units to Fourier layers, they are basically very, very similar. But what the unit is doing within one architecture, the Fourier layer is doing in one layer. Because a Fourier transform is nothing else than using your signal and transforming it in different modes. So you have the low modes, which correspond to global information, and the very high modes, which correspond to local information. And if you multiply these different ranges of modes, these different modes, you basically mix global and local information together, and then you transform back. So this different treatment of global and local information in units and Fourier neural operators is quite striking, I would say. And then there is another thing which is very interesting. If you sorry, I'm going back. If you look at this neural at these units, you basically see that you have this clear downsampling pattern. And what we know from computer vision, that downsampling always comes with some aliasing effects. So basically, this is an original image of a tiger, and taken from the paper of my colleagues Daniel Warren and Max Welling. And if you basically just take every 8th pixel, I think they did, you end up with this very hard to recognize tiger. But if you basically Fourier transform this tiger and cut away the high frequency information, and then on this band limited sample do the downsampling, you get a much better version of a downsampling tiger. So the question is, why not use this Fourier blocks basically in combination with these units in this high blocks where you actually really need a good downsampling? And that basically brought us to the realization that there's so many, that the space of architecture design is huge. So we basically build a big model zoo where we really have a very different ways of Fourier neural operators, of resonance, of dilated resonance, which are also quite interesting in the way that they treat global information, and many unit variants. And we basically check them on number of parameters, forward pass, backward pass, memory efficiency, peak usage, and so on and so forth. And we tried that on different equations, so Navier-Stokes in 2 different formulations, Scheller-Watt equation as seen before, but also, and that is the interesting stuff, it should learn to predict Navier-Stokes for different parameters, for different time scales, and so on and so forth, because this is the conditioning which is actually done in computer vision. And the results were quite interesting for us, because it really seems that these modern unit variants strike back. So there's tons of experiments. Again, on the left side, there's a small number of training samples where you see that actually there's not so much difference between the models. And on the right, there's a huge training set. And you see basically that all these parts on the left, on the right, are some kind of units with different versions of downsampling, different versions of attention layers, and so on and so forth. So it really seems that these units also do a fantastic job in PDE modeling, which was quite interesting. And that's just an example of one prediction where as before, you have the scalar fields, and you basically predict the scalar fields 5 times into the future, and you see basically that it really follows the ground truth very well and with very high resolution. You do the same for the vector fields. So these are just the components of the vector fields plotted individually to visualize. And lastly, I want to say what I mean with this parameter conditioning. So we have here like 2 blocks. The block on the left is an experiment setting with a Biot-C force term, so force term of 0.2, and on the right with 0.5. And then we see on the y-axis different delta t, so different time windows. And each of these plots, so where we have the ground truth on the left and the prediction in the middle, is basically created from the same input data, but the conditioning on these parameters is different. So we have once the input data where we say I want 1.5 seconds into the future with a Biot-C force of 0.2. Then we have the conditioning I want 1.7 seconds into the future with a Biot-C force of 0.5. And that seems to work very well. And that is very reassuring, because this is one of these requirements we have for neural PDE solvers or surrogates, that they really help that we don't have to do every calculation or every training from scratch, but that we can learn to generalize it across a bunch of models, a bunch of parameters and equations. And that already brings me to the recap. Well, I tried to basically split this this down into two parts, where the overall theme is that the PDE modeling needs more geometry and structures, where the Clifford layers, of course, try to enforce structure, and the local and global information, especially this very interesting way of how Fourier transforms and units operate, is I tried to cover in my second part. And then, of course, there is this pressing question. I think people will ask, why didn't you combine units with Clifford layers? You can guess that is actually what we are doing right now. And that the whole theme also should be to really start that people use this really state-of-the-art units from computer vision as benchmarks for whatever they do. And therefore we try to put out a framework on GitHub, which is all has all these models in on these data sets, and you can try them yourself and plug in any models you want, and basically see what is going on. And we will also output the Clifford library, such that people can start using that as well. And that is the end of my talk. Most of this work is done together with my fantastic colleague Jayesh Gupta from Seattle, and we're very happy to answer questions anytime.
Wonderful, thank you so much. So normally we do not record a Q&A, so everyone feels comfortable, opening their mic and asking questions. So I'll stop the recording now, and then we'll start a